Hello everyone. This chapter focuses on the technical principles of MapReduce and Young. After this course, we'll be able to know concepts of MapReduce and Young, application scenarios and principles of MapReduce, functions and architectures of MapReduce and Young, and also I'll talk about some new features of Young. First, let's take a look at the introduction to MapReduce and Young. Well, MapReduce is a processing technique and a program model for distributed parallel computing of a massive dataset. The advantages of MapReduce include that it's easy to program. Programmers only need to describe what to do, and the execution framework will do the job accordingly. And it's easy to scale data processing over multiple computing nodes. We can just simply add nodes to improve cluster capabilities. Besides, MapReduce is highly fault-tolerant. If one of the nodes in the cluster fails, tasks running on the node can be performed on another node using computer migration or data migration to ensure successful execution of tasks. And Young, yet another resource negotiator, is Hadoop's Cluster Resource Manager, providing resource management and scheduling for upper-layer applications. Why say another? Actually, there is a resource negotiator before Young, but it has many limitations, and it's not used anymore. So here I don't talk about it too much. Take a look at the architecture of Fusion inside Hadoop. At the bottom is HDFS, which is the storage infrastructure. On top of HDFS is Young, which is used for managing and scheduling resources for applications. Then, there are some computing engines above Young, like MapReduce, Spark, and Hive. When these computing engines are working, they need to apply resources from Young. So in this case, administrators do not need to maintain resource manager for each computing engine. They only need to maintain Young, which reduces the operation and maintenance cost. Besides, the whole cluster shares the resources so that they can be highly used. Then, let's take a look at the functions and architectures of MapReduce and Young. How does the process of MapReduce work? Let's take a look. At first, MapReduce submits requests to Resource Manager. Resource Manager is responsible for the unified management and allocation of all resources in the cluster. It's a component of Young. Then, Resource Manager creates jobs. But before jobs are submitted, the files to be processed need to be split. MapReduce regards a block as a split by default, and the client applications can also redefine the mapping relation between blocks and splits. For example, assume that a file is stored as 3 blocks in HDFS. When we use MapReduce to process this file, the file will be divided into 3 splits. Each block corresponds to a split, and each split corresponds to a map task. That is, a map task can only process a split. The number of splits determines that of map tasks created for the job. And after the jobs are submitted to Resource Manager allocates resources for them. It selects an appropriate node manager in the cluster to schedule application masters based on the workloads of node managers. Here, node manager is the agent on each node, and application master is responsible for all the jobs within the application lifecycle. So after a node manager is selected, application master initiates jobs and applies for resources from resource manager, and the selected node manager will start the container for task execution. Then is the process of map task. The map task takes a set of data and converts it into another set of data, where individual elements are broken down into key value pairs. Each map task has a circular memory buffer that it writes the output to. The buffer is 100 MB by default. The size can be configured by user. When the contents of the buffer reach a certain threshold size, which by default is 80%, data in the buffer will be written to local disks. Before it writes to disk, the following process must be completed. First, data is divided into partitions. The number of reduced tasks is determined by clients, and the number of partitions is determined by that of reduced tasks. And data with the same key value are sent to the same reduced tasks for processing. Within each partition, map output will be sorted by key, combined if necessary, and merged as a map out file. Each time the memory buffer reaches the spill threshold, a new spill file is created. So after the map task has written its last output record, there could be several spill files. Before the task is finished, the spill files are merged into a single partitioned and sorted output file. This file is the map out file. When map tasks are finished and the output progress of MOF reaches 3%, the reduced tasks are started and copy MOF files from each map task. The reduced task needs the map output for its particular partition from several map tasks across the cluster. The map tasks may finish at different times, so the reduced task starts copying their outputs as soon as each complete. Then, reduced tasks sort and merge multiple map-out files into one. During the reduce phase, the reduce function is invoked for each key in the sorted output. The output of this phase is written directly to the output file system, typically HDFS. Here, let me add another concept called shuffle. It's the data transfer process between the map task and the reduce task, which involves that reduce tasks copy MOF files from the map tasks and then sort and merge MOF files. Let's take a typical program word count as an example to better understand the working process of MapReduce. This program defines its own map and reduce functions that can analyze the times of each word repeated in a file. So for example, when we use the word count program to count the number of each word repeated in file A, the process is as follows. First, we need to make sure that file A to be processed is stored in HDFS and divided into blocks A1, A2, and A3, which are stored on data node 1, 2, and 3 separately. Then, the program submits applications to Resource Manager. The Resource Manager creates jobs based on the request and creates 3 map tasks as well as 3 reduce tasks that are running in containers based on the number of blocks. The output of map task is an MOF file that is partitioned and sorted but not combined. And then, reduce tasks obtain the MOF from map tasks after combination, sorting, and user-defined reduce function processing. The output result is shown in the table 4. Let's see the detailed process of map task and reduce task. This figure shows the function of word count program. this is the result that we want. Assume the file that contains words is stored as 3 blocks in HDFS. So, there are 3 map tasks based on the number of splits. Each map task generates an output like this in key-value pairs. And then we combine the results in each map output and do the shuffle, which is to copy MOF from map task and sort, merge into one file like this. And then use user-defined reduce functions to process the reduce input. That finally creates a reduced output. Next, let's see the architecture of Yang. It consists of the following components: client, resource manager, node manager, application master, and container. Client is to submit jobs to resource manager. A resource manager is used to manage the use of resources across the cluster. There is only one resource manager in a Hadoop cluster. And node managers are running on all nodes in the cluster to launch and monitor containers, which also report node status to resource manager periodically. Application master is responsible for negotiating resources from the resource manager and working with the node manager to execute and monitor the component tasks. And a container is an abstraction of Yang resources, and it executes an application-specific process with a constrained set of resources, including memory and CPU. And it reports the status of MapReduce tasks to application master. So when a client submits a job to resource manager, the resource manager receives the job and allocates the first container for the application program and asks node manager to start application master in the container. Then, application master registers with the resource manager so users can directly view the operating status of the application programs. After that, application master applies for and obtains resources from resource manager in pooling mode using the RPC protocol for each task and monitors the tasks until finished. Once obtaining resources, application master asks node manager to start the tasks. Then, node managers start the tasks. Each task uses RPC to report its status and progress to application master, so that application master can restart the task if one fails. During the running of the application program, users can use RPC to obtain the operating status of the application program from application master at any time. After the application program ends, application master cancels its registration with the resource manager and closes itself. So, this is the whole task scheduling of MapReduce on Yang. Resource Manager in Yang also uses an active standby architecture, which ensures high availability. Similar to the HDFS HA solution, when the active Resource Manager fails, the failover can be triggered automatically or manually to switch active and standby state. When automatic failover is not enabled, administrators must run a command to manually switch one of the Resource Manager nodes to the active state. When the active Resource Manager goes down or becomes unresponsive, another Resource Manager is automatically elected to be the active node that then takes over services. In Yang, application master may break down, exit, or shut down for various reasons. If an application master goes down, Resource Manager will close all the containers that it manages. including containers where tasks are running. And Resource Manager will start a new application master on another computing node. But for services that run for a long time, users do not wish the whole service stops because of the failure of an application master. Therefore, Yang supports the feature of preserving the container status when starting a new application master so that the tasks in these containers can run continuously without any failure. Next, let's take a look at resource management and task scheduling of Yang. Now, Yang supports management and allocation of two types of resources, memory and CPU. Users can configure the memory and the number of CPU for each node manager. The first configuration indicates the physical memory size of the container running on node manager, expressed in megabytes. The value must be smaller than the memory size of the node manager server. And the second one indicates the ratio of the maximum available virtual memory to the physical memory of a container. The assigned container memory usage is specified based on physical memory. The proportion of virtual memory utilization exceeding the assigned value is not allowed to be greater than that ratio. And the third one indicates the number of CPU cores that can be allocated to a container. It's recommended that this parameter value to be set to 1.5 to 2 times the number of CPU cores. Let's see how the resources are allocated by Yang. Well, in Yang, resource schedulers organize resources through hierarchical queues. This ensures that resources are allocated and shared among queues, thereby improving the usage of cluster resources. To be more specific, Resource Scheduler in Resource Manager maintains information of a cluster of queues. Users can submit applications to one or more queues. Then, Resource Scheduler selects a queue based on certain algorithms and selects an application in the queue, and then attempts to allocate requested resources to the application. Here, queues are subsets of the whole cluster resources. Queues are classified into parent queues and child queues, or we can say leaf queues. A parent queue can have multiple leaf queues. Tasks are running on leaf queues. If a queue is specified when a task is submitted, the scheduler allocates the task to the queue. If no queue is specified, the task is allocated to the default queue. If resources fail to be allocated to an application due to the limit of some parameters, the resource scheduler will select the next application. After the scheduler selects an application, the application may manage many resource requests. The scheduler first satisfies the request for local resources, and then for resources on the same rack, and finally for resources from any machine. The capacity scheduler is designed to run Hadoop applications as a shared multi-tenant cluster in an operator-friendly manner while maximizing the throughput and the utilization of the cluster. Traditionally, each organization has its own private set of compute resources that have sufficient capacity to meet the organization's service level agreement under peak or near-peak conditions. This generally leads to poor average utilization and overhead of managing multiple independent clusters. The capacity scheduler also provides a strict set of limits to ensure that a single application or a user or a queue cannot consume disproportionate amount of resources in the cluster. Administrators can restrict the resource used by a queue, user, or a job. The capacity scheduler supports the following features. Capacity assurance. All applications submitted to a queue will have access to the resource capacity allocated to the queue. Administrators can configure soft limits and optional hard limits on the capacity allocated to each queue. Flexibility. Temporarily, resource supplies of a queue can be shared with other queues. However, such resources must be released in case of new application submission to the queue. Such flexible resource allocation helps notably improve resource usage. Priority. This feature allows applications to be submitted and scheduled with different priorities. Higher integer value indicates higher priority for an application. Currently, application priority is supported only for FIFO ordering policy. Multi-listing. Comprehensive set of limits are provided to prevent a single application, user, or queue from monopolizing resources of the queue or the cluster as a whole to ensure that the cluster is not overwhelmed. Dynamic update of configuration files. As the administrator, you can dynamically modify configuration parameters as required to achieve online cluster management. There are two steps for task selection by capacity scheduler. The capacity scheduler selects an appropriate queue first and then selects a task from the queue. The queue is selected based on the following policies. The queue with the lower resource usage is allocated first. For example, you have two queues, Q1 and Q2, and both have the same capacities, let's say 30, and the used capacity of Q1 is 10 and Q2 is 12. Then, resources are allocated to Q1 first. Resources are allocated to the queue with the minimum queue hierarchy first, and the resources are allocated to the resource reclamation request queue first. A task is then selected based on the task priority and submission sequence as well as the limits of user resources and memory. In Fusion Insight platform, users can create queues by Fusion Insight Manager. Here shows a web page of tenant management in Fusion Insight Manager. When creating a tenant and associating with Yang, a queue with the same name as tenant will be created. Log into Fusion Insight Manager and choose Tenant, Dynamic Resource Plan, Resource Distribution Policy. We can see the following page. The resource allocation area shows the resource capacity for each queue. The resource capacity of queues can be configured by users. By default, the capacity of the default queue is 20% of the total cluster resources, and the capacity of the new queues is 10% of the total cluster resources if user does not modify the default configuration. And there is a shadow queue in the background. A shadow queue is named XXDefault, which is invisible. The remaining resources of the cluster are allocated to this queue. The resources used by a queue may exceed its capacity due to resource sharing. The maximum resource usage can be limited by parameter, which is set to 100 by default. For example, if the maximum capacity of QA is set to 100, and there are only tasks running in QA, theoretically, QA can use all the cluster resources. Besides, Yang supports to limit users and tasks. We can configure the user and task limitation parameters by Fusion Insight Manager in the QConfig page. While for user limitation, which indicates the resource usage restrictions for users, there are two parameters. First is minimum resource assurance of a user. When there are multiple tasks of different users running at the same time in a queue, the available resources for each user is between the minimum value and the maximum value. The maximum value is determined by the number of running tasks, and the minimum value is determined by this parameter, minimum user limit %, which is set by users. For example, let's set this parameter to 25 for QA. Then, when first user submits jobs to QA, he will obtain 100% of the resources in QA. And then, second user submits jobs. Each user will obtain 50% of the resources at most, and then 33.3% at most when the third user submits jobs. If this continues, when the fifth user submits jobs, he cannot obtain any resources and must wait for them to be released by other users, because this parameter ensures that each user can obtain 25% resources at least. And the second parameter is maximum resource usage of a user, which means the multiples of queue capacity. For example, if we set this parameter to 1, which is by default, the resource obtained by user cannot exceed the queue capacity. Remember that the resource obtained by user can exceed the resource capacity, but must not exceed the maximum capacity. As for task limitation, there are three parameters. Maximum number of active tasks. The default value is 10,000. When the number of submitted task requests reaches 10,000, new tasks will be rejected. Second is maximum number of tasks in a queue. The default number is 1,000. If the number of submitted task requests in QA reaches 1,000, new tasks will also be rejected. And third is maximum number of tasks submitted by a user. This parameter depends on the maximum number of tasks in a queue. For each user, the maximum number of tasks submitted is the product of three parameters, which is the maximum number of tasks in a queue, minimum resource assurance of a user, and the maximum resource usage of a user. After configuration, users can view the information queue by Fusion Insight Manager Web UI. This figure shows the information of QA, including used capacity, configured capacity, and so on. The last part is the enhanced features of Yang in Fusion Insight. First one is dynamic memory management. This feature is used to optimize the memory usage of containers in Node Manager. While in earlier version of Yang, Node Manager will queue the containers that exceed the container's memory threshold, even though total configured memory utilization of the node is low. As a result, consumer jobs fail frequently. So in order to improve this, Fusion Insight adds another judgment method, which is to queue overused container only when the overall memory usage of all containers in Node Manager reaches a certain threshold value. This value is the memory threshold set for Node Manager, which can be calculated as follows. The other one is label-based scheduling. Before label-based scheduling is used, it's impossible to control which node a task is submitted to. Tasks are allocated to nodes based on some algorithms and conditions. Label-based scheduling can specify the nodes to which tasks are submitted. But there are some scenarios that applications may need special computing resources. For example, there are applications that have demanding memory requirements, but due to uncontrollable task submission, these tasks may run on servers with standard performance. So in this case, Fusion Inside Yarn schedules tasks based on labels. Users are able to label each node manager, for example, labeling node manager with high memory or high I/O. In the meantime, users can label each queue in the scheduler. That is, queues are bounded with labels. Jobs submitted to a queue use resources on the labeled node, so tasks are running on labeled nodes. For example, those tasks that have demanding memory requirements will be submitted to queues with high memory labels, so that tasks can run on servers with large memory. So this chapter mainly talks about application scenarios and architectures of MapReduce and Yarn, resource management and task scheduling of Yarn, and also some enhanced features of Yarn in Fusion Inside HD. Okay, that's all for MapReduce and Yarn. Thank you. Does Spark provide? Spark provides a one-stop data analysis capability and supports flow-based processing in small batches, offline batch processing, SQL query and data mining, graph computing, and machine learning. Users can seamlessly use these functions in an application. In practical use, for example, batch processing can be used for data ETL, which is to extract, transform, and load data. Machine learning can be used for shopping websites to judge whether customer reviews are good or bad. And SQL query can be used for query data in Hive. And stream processing is applicable for real-time services, such as clickstream analysis, recommendation system, and public opinion analysis. Take a look at some key features of Spark. First, light. Spark uses Scala language, which is much more simple and vivid. Besides, it uses infrastructure of Hadoop and Mesos, which is also an open-source framework to manage computer clusters. So Spark has only 30,000 lines of core code. Second, fast. Spark has sub-second level latency for a small dataset. Specifically, Spark has higher speed compared with MapReduce or Hive for large dataset applications such as iterative machine learning, ad hoc query, and graph computing. Besides, Spark is featured with in-memory computing, data locality and transmission optimization, and scheduling optimization. Third, flexible. Spark provides flexibility at different levels. For example, Spark supports new data operators, new data sources, and new language bindings. And Spark supports a variety of functions, such as in-memory computing, multi-iteration batch processing, ad hoc query, streaming, and graph computing. The last one is smart. It uses existing big data components. To be more specific, Spark seamlessly integrates with Hadoop, and graph computing uses Prego, Power Graph APIs, as well as Power Graph point of division. Prego and Power Graph both are distributed graph parallel computing framework. Based on this figure, we can see that Spark is capable of interacting with multiple applications, environments, or different data sources, such as Hive, Apache Hadoop, and MySQL HBase. We've learned MapReduce before. It's also a computing model framework, and it's used for parallel computing of a massive dataset. And in MapReduce, intermediate data generated by map tasks will be written to local disks as MOF, which is map out files, waiting to be obtained by reduce tasks. But the intermediate data of Spark is stored in memory. So Spark improves the computing efficiency and reduces the delay of iterative operations and batch processing. Besides, Spark is suitable for iterative computation. If repeated operations increase, more data needs to be read, and Spark computing brings greater benefits because intermediate data of Spark is stored in memory. So the performance of Spark is over 100 times higher than that of MapReduce in specific scenarios with multiple iterations. For scenarios with fewer iterations, Spark does not have many advantages over MapReduce. Spark also provides more flexible programming model and higher development efficiency because Spark provides more dataset operation types. And Spark has higher fault tolerance capability because of lineage mechanism. I'll explain this mechanism later. Take a look at this figure to show the difference more intuitively. In MapReduce, we read data from HDFS. After first iterative computing, we'll save the intermediate result on the disk. Then, make second processing. Results of every iterative computing need to be written in disk. But in Spark, intermediate results do not need to be written in disk. It's stored in distributed memory, which improves the computation performance. And this table shows that the performance of Spark is much better than that of MapReduce. The resources, including the number of nodes and cores needed for computing in MapReduce, is almost 10 times of that in Spark. But Spark provides the performance by more than 3 times. Next, let's talk about Spark principles and architecture. The first one is Spark Core. This is the system architecture of Spark. The green part is the new function of Spark version 2. At the bottom is the standalone scheduler, which is a resource management framework that comes with Spark. It also supports the resource management systems of Yarn and Mesos. But Fusion Insight integrates the Spark on Yarn mode by default and does not support other modes currently. In the middle is Spark Core. It's a distributed computing framework similar to MapReduce. The intermediate computation result is directly stored in memory, which improves the computation performance. On top are some functional modules. Spark SQL is a Spark component mainly for processing structured data and conducting SQL-like queries on data. By using the Spark SQL, ETL operations can be executed based on different data formats, such as JSON, Parquet, and ORC, and data sources, like HDFS and database, to complete specific query operations. Structured streaming is an engine built on Spark SQL to process streaming data. It's programmed by using Scalar and is fault-tolerant. Spark Streaming is a streaming engine for micro-batch processing. Stream data is sliced and then processed in the computation engine of Spark core. Compared with Storm, it provides weaker real-time performance, but better throughput. And MLlib is Spark's machine learning library. Its goal is to make practical machine learning scalable and easy. GraphX is a new component in Spark for graphs and graph parallel computing. GraphX includes a growing collection of graph algorithms and builders to simplify graph analytics tasks. Sparkr is an R package that provides a lightweight front end to use Apache Spark from R. In Spark version 2, Sparkr provides a distributed data frame implementation that supports operations like selection, filtering, aggregation, and so on large datasets. Sparkr also supports distributed machine learning using MLlib. Spark revolves around the concept of RDD, which is Resilient Distributed Dataset. RDD is a fundamental data structure of Spark. It's a read-only partitioned collection of records. RDDs are stored in memory by default and will overflow to disks in case of insufficient memory. Each RDD is divided into logical partitions, which may be computed on different nodes of the cluster. This feature improves performance by data locality. There are two ways to create RDDs. An RDD can be created from a Hadoop file system such as HDFS, or a storage system that Hadoop is compatible with. Alternatively, an RDD can be converted from a parent RDD. Besides, RDD supports a lineage mechanism, which indicates the dependency chain. An RDD remembers how it's evolved from another RDD using a lineage. So in this case, data can be recovered quickly when data loss occurs. There are two types of dependency of RDD, narrow dependencies and wide dependencies. Narrow dependency indicates that each partition of the parent RDD is used at most by one partition of the child RDD, while wide dependencies indicates that each partition of the parent RDD may be used by multiple child RDD partitions, which is the basis of state division. There are some advantages of narrow dependency. First, narrow dependency supports execution of multiple commands in pipeline mode on the same cluster node. For example, after the map operation is performed, the filter operation can be performed immediately. Second, failure recovery of narrow dependency is more effective because only the lost parent partition needs to be recomputed, and the recomputation can be performed concurrently on different nodes. It's very difficult to divide stages in a submitted job due to complex RDD dependencies. In this case, Spark uses narrow dependencies and wide dependencies that are mentioned before. Spark Scheduler reversely traverses the whole dependency chain from the end of the DAG. When a wide dependency is encountered, the dependency chain is broken. When a narrow dependency is encountered, the RDD partition is added to the current stage. The number of tasks in a stage is determined by the number of RDD partitions at the end of stage. RDD conversion is a partition-based coarse-grained computing, and the result of a stage execution is the RDD of these partitions. RDDs support two types of operations, transformation and action. For example, map is a transformation that passes each dataset element through a function and returns a new RDD representing the results. On the other hand, reduce is an action that aggregates all the elements of the RDD using some function and returns the final result to the driver program. All transformations in Spark are lazy, in that they do not compute their results right away. Instead, they just remember the transformations applied to some datasets or files. The transformations are only computed when an action requires the result to be returned to the driver program. This design enables Spark to run more efficiently. For example, we can realize that a dataset created through map task will be used in a reduce task and return only the result of the reduce task to the driver, rather than the larger mapped dataset. Then let me introduce some major roles of Spark. Driver is responsible for the application business logic and operation planning. Application master is used to manage application resources and applies for resources based on applications. Client is to submit applications. Resource manager is responsible for scheduling and allocation of resources in the whole cluster, and node manager is responsible for resource management of each node. Executor is the one that really do the tasks. An application will be split for multiple executors to compute. The Spark computing and scheduling can be implemented using Young mode. Spark enjoys the computing resources provided by Young clusters and runs tasks in a distributed way. Spark on Young involves two modes, Young client and Young cluster. In Young client mode, the driver is deployed and runs on the client. During the operation process, the client first sends the Spark application request to Resource Manager, and the client packages all the information required to start Application Master and sends the information to Resource Manager. Then, Resource Manager returns the results. The results include information such as application ID and the upper limit as well as lower limit of available resources. After receiving the request, Resource Manager finds a proper node for Application Master and starts it on its node. Application Master is a role in Young, and the process name in Spark is Executor Launcher. Based on the resource requirements of each task, Application Master can apply for a series of containers to run tasks from Resource Manager. After receiving the newly allocated container list from Resource Manager, Application Master sends information to the related Node Manager to start the container. Resource Manager allocates a container to Application Master. Then, Application Master communicates with the related Node Manager and starts Executor on the obtained container. After Executor is started, it registers in Driver and applies for tasks. Then, Driver allocates tasks to Executor. Executors do the tasks and report the operating status to Driver. And the Spark on Young cluster implementation process is as follows. Client first generates the application information and then sends the information to Resource Manager. The Resource Manager allocates a container to Spark application and then starts Driver on the container node. After that, Application Master applies for resources from Resource Manager to run Executor. The Resource Manager allocates a container to Application Master. Application Master communicates with the related Node Manager and starts Executor on the obtained container. After Executor is started, it registers in Driver and applies for tasks. Then, Driver allocates tasks to executors and executors do the jobs and report the status to driver. So what's the difference between young client mode and young cluster mode? The first one is application master. In young cluster mode, drivers runs in application master, which is responsible for applying resources from young and monitoring the running status of a job. When a user submits a job, client can be closed and the job continues running on young. However, the young cluster mode is not suitable for running interactive jobs. In young client mode, application master applies only executor from young. Client communicates with the obtained container to schedule tasks. Therefore, client cannot be closed. And young cluster is suitable for production because the outputs of applications can be quickly generated, while young client is suitable for testing. Besides, if the task submission node in young client mode is down, then the entire task will fail. But this kind of situation in young cluster mode will not affect the entire task. Let's take a look at a typical case word count based on Spark. At first, use command text file to obtain data from HDFS and process in the form of RDD. Then, invoke flag map to split text into words. And then do map operation to denote the frequency of appearance of each word as one. And then invoke reduce by key to merge the counts of each word. And finally invoke save as text file to import process data into HDFS. Here, until the save as text file command is executed, the whole Spark computing processing is starting. All the four previous operators are the transformation operators, and only the save as text file is the action operator. The next part is about Spark SQL and dataset. Spark SQL is a module for processing structured data. In Spark application, SQL statements or data frame APIs can be seamlessly used for querying structured data. Simply speaking, Spark SQL is just a module that can parse SQL language to RDDs and then use Spark Core to execute. This graph here is to show you the process of parsing SQL language to RDDs. Here, data frame is a distributed collection in which data is organized into named columns. Spark SQL and data frame also provide a universal method for accessing multiple data sources such as Hive, CSV, ORC, and JSON. These data sources also allow data interaction. Spark SQL reuses the Hive front-end processing logic and metadata processing module. With the Spark SQL, you can directly query existing Hive data. In addition, Spark SQL also provides API, CLI, and JDBC interfaces, allowing diverse inputs to the client. A dataset is a strongly typed collection of domain-specific objects that can be transformed in parallel using functional or relational operations. Datasets are similar to RDD, but does not use Java serialization or Creo encoders to serialize objects for processing or transmission over the network. Encoders and standard serialization are responsible for serializing an object into bytes. Encoders dynamically generate code and use a format that allows Spark to perform many operations, such as filter, sort, and hash without deserialization bytes into objects. Each dataset also has an untyped view called a data frame, which is a dataset of row. Data frame is a structured distributed dataset composed of several columns, which is similar to a table in the relational database or the data frame in R or Python. Data frame is a basic concept in Spark SQL and can be created by using multiple methods, such as structured dataset, Hive table, external database, or RDD. Data frame has data structure information, which is schema. RDD, datasets, and data frame are compared. For RDD, both cluster communication and I/O operations require serialization and deserialization of data and data structures. Datasets and data frame have exactly the same functions, but the different types of the data in each row. For data frame, data in each row is of the row type. Fields and types of these fields in each row are unknown. You can only use getAs or pattern matching in the comment to obtain a specific field. In a dataset, the type of each row is not fixed. After defining the case class, you can obtain the information in each row. Information in columns of data frame is clear, but that in rows are unclear. Compare Spark SQL with Hive. Spark SQL uses Spark Core as its execution engine, while Hive uses MapReduce. And the execution speed of Spark SQL is 10 to 100 times faster than Hive. Spark SQL syntax and Hive syntax are basically the same except for bucket operations. Besides, Spark SQL depends on the metadata of Hive, and it's compatible with most syntax and functions of Hive. It can also use user-defined functions in Hive. Then, let's take a look at Spark structured streaming. Well, structured streaming is an engine built on Spark SQL to process streaming data. It's programmed by using Scalar and is of fault tolerance capability. Streaming computing processes are compiled similar to the application of static RDD data. If streaming data is incrementally and continuously produced, Spark SQL will continue to process the data and synchronize the result to the result set. Similar to the data block processing model, the streaming data processing model applies query operations on a static database table to streaming computing, and Spark uses standard SQL statements for query to obtain data from the incremental and unbounded table. Consider the input data string as the input table. Every data item that is arriving on the string is like a new row being appended to the input table. Each query operation will generate a result table. At each trigger interval, updated data will be synchronized to the result table. Whenever the result table is updated, the updated result will be written into an external storage system. And there are three types of storage modes of structured streaming at the output phase: complete mode, append mode, and update mode. For complete mode, a connector of an external system writes the updated result set into the external storage system. For append mode, if an interval is triggered, only added data in the result table will be written into an external system. This mode is applicable only to a result set that has already existed and will not be updated. For update mode, if an interval is triggered, only updated data in the result table will be written into an external system, which is the difference between the append mode and update mode. To illustrate the use of this model, let's understand the model in context of the word count example here. The first line's data frame is the input table. and the final word counts data frame is the result table. Note that the query on streaming line's data frame to generate word counts is exactly the same as it would be a static data frame. However, when this query is started, Spark will continuously check for new data from the socket connection. If there is new data, Spark will run an incremental query that combines the previous running counts with the new data to compute updated counts, as shown here. Note that structured streaming does not materialize the entire table. It reads the latest available data from the streaming data source, processes it incrementally to update the result, and then discards the source data. It only keeps around the minimal intermediate state data as required to update the result, such as the intermediate counts in this example. The last one is Spark streaming. Spark streaming is a real-time computing framework built on the Spark, which expands the capability for processing massive streaming data. Data can be ingested from many sources like Kafka, HDFS, and can be processed using complex algorithms expressed with high-level functions like map, reduce, join, and window. Finally, processed data can be pushed out to file systems and databases. The basic principles of Spark streaming is to segment the input data by second or millisecond, and periodically submits the data after segmentation, which decomposes streaming programming into a series of short batch jobs. While simply speaking, it works as follows. Spark streaming receives live input data streams and divides the data into batches, and then are processed by the Spark engine to generate the final string of results in batches. One more thing to notice is that Spark streaming provides a high-level abstraction called discretized string or dstring, which represents a continuous string of data. These streams can be created either from input data streams from sources such as Kafka, Flume, or by applying high-level operations on other dstreams. Internally, a dstring is represented as a sequence of RDDs. Spark streaming performs computing based on RDDs, so any partition encountering errors can be regenerated based on the parent RDD, using the RDD lineage mechanism. If the parent RDD is lost, look up for its parent RDD until the original data in the disk is found. At last, let's take a look at the Spark integration in Fusion Insight HD. Fusion Insight Manager provides a virtual web UI for Spark, allowing users to obtain information about the service status, roles, and open configuration items, perform management operations such as starting and stopping Spark, downloading the Spark client, and synchronize configurations, and also can view the running instance health status and service overview. In the Fusion Insight cluster, Spark interacts with the following components. For example, Spark reads or writes data in HDFS, Yang schedules and manages resources to support the running of Spark tasks. Spark SQL shares metadata and data files with Hive, and HA of JDBC server depends on the coordination of Zookeeper. JDBC server provides the JDBC interface for directly sending external JDBC requests to compute and parse structured data. The first four are mandatory. Besides, Spark can receive data streams sent by Kafka, and it can perform operations on edge-based tables. These two are optional. So this chapter mainly talks about Spark, including its background, application scenarios and characteristics, basic concepts, technical architecture, task running process, Spark on Yarn, and application scheduling. Also, I've introduced the integration of Spark in Fusion inside HD. Okay, that's all for Spark. Thank you.